So we can consider the three cases. So for example, this is the bulk, the metal oxide. Then we can deposit small particle on this metal oxide surface, right? Then also we can consider second case, the submerged case. In this case, we cannot see any the catalytic activity. Then last case is an exsolution, so exsolute case. So you can see tightly the anchor catalytic property. It looks like the socket-like structure, okay? So how we can get this structure? So we can incorporate the element, heteroatom atom, the doping. Then after the reducing atmosphere annealing, this doped element exsoled and segregated, forming exsolute catalyst. So you can see here, right? But most case, this is a bulk material, then small catalyst decorated on our surface, then high temperature operation, they will aggregate it, right? Agglomerating, eventually detached from the support layer. That's why this kind of exsolution, the catalyst design is very important. So as I mentioned, but this exsolution usually occur at very high temperature, over 700 degrees C, then highly the reducing atmosphere. Then you can imagine the furnace annealing system, right? So lamping, temperature duration, and cooling. It takes very long time, right? So 10 hours, sometimes over the 1 day. So we want to be interested in the reduction of this processing time. So that's why we demonstrate the low dimensional material, for example, 2-dimensional nanostructure, and also zero dimensional ZIF-A driven porous zinc oxide. By using this, the nanostructure will significantly reduce the exsolution temperature. For example, iridium doped tungsten oxide and 300 degrees C exsolution was observed. Then once we increase the annealing temperature 400, 500, this small catalytic particle grow, then become a relatively larger particle. We reduce the temperature 300 degrees C, 500 degrees C, but still high temperature. So that's why we are interested in the mechanically stable, thermally stable catalyst design, then also the ultra-fast processing using Joule heating and flash thermal shock synthesis. So today I'm going to see very thin, like the 5 nanometer thickness titanium oxide conformally coated on. And Professor Jury from MIT, they used electrospun carbon nanofiber. After then, they coat the metal salt on the carbon nanofiber surface, right? So 2 precursors, 8 precursors, mixed precursors. Then after the Joule heating, in this schematic, you can see y-axis is temperature and x-axis is shock time. So here, this is 60 millisecond, 0.06 second. Very fast, right? Then after the rapid cooling, almost quenching. So in this case, there is no time for phase separation. Then we expect high entropy alloy catalyst design. Then when I read this article, I was really interested. Then I decided to, okay, so let's prepare or let's make our own the Joule heating setup. Then it takes so long time, almost 3 years. We carefully control the oxygen partial pressure, and this is our Joule heating setup. And we first prepare our own carbon nanofiber. Then we connected this fiber with a copper foil. Then you can see this is a silver paste, right? Then we apply the bias in current. Temperature increase up to almost 1,500 degrees C. We can control the pulse, for example, 4-second long duration pulse, then also short pulse, multiple pulse. Then also you can see here relatively large area, so we can cover 10 centimeter and 10 centimeter carbon nanofiber beyond. Simply by coating the 2 precursors, for example, platinum precursors, palladium precursors, mixed precursors, then apply the bias current. Then you can see platinum, palladium, bimetallic catalyst particles simply synthesized on carbon fibers. 3 precursors, ternary alloy particle, 4 precursors, quaternary alloy particle. This small particle just attached on carbon fiber, right? So let's increase the temperature up to 600 degrees C. What happened? Can you guess? Yes, this small particle will be aggregated, right? Then eventually detached. So that's why we're interested in how we can prevent this aggregation of agglomeration. Then we prepare the high density, the nanofiber yarn. Let me explain that later. Then after polymer nanofiber yarn synthesis, then we anneal this fiber in the reducing atmosphere to synthesize carbon, the nanofiber yarn. After that, we first coat here, example, the titanium precursors. Then first step, Joule heating to synthesize titanium oxide overlayer. After that, we mixed 5 precursors, the metal salt, metal ion, and directly coated on this titanium oxide overlayer. Actually, this titanium oxide is a super hydrophilic, so these salts are well coated on our surface. And second step, Joule heating, and surprisingly, these small high entropy alloy particles are well embedded within titanium oxide overlayer. So simply, we counted particle size about 2.4 nanometers. A lot of particles you can see here, right? More than thousands of particles are well embedded in titanium oxide support layer. Without oxide support layer, you can see, although the small particles are well formed, but certain area is not well covered, right? But by introduction of this titanium oxide overlayer, you can see even particle distribution. They are well anchored. Looks like those structures. So we apply this catalyst material for the CO2 conversion efficiency. So actually, this CO2 conversion occurred at 600 degrees C, fairly high temperature considering such a small particle, right? 2.4 nanometer. Then, as you can see here, without catalyst titanium oxide, there is no CO2 conversion. Then, only high entropy alloy particle decorated CNF, they show small conversion efficiency, 20%, but 1 day later, they gone, right? Then, but in the case of titanium oxide supported high entropy alloy catalyst, it shows almost 60%. But more importantly, they maintain their morphology even after 300 hours, right? So this is a really extremely harsh condition, but our well-designed nanoparticles are maintained after this harsh operation. So I explained the carbon thermal shock synthesis, right? So in order to use this carbon thermal shock, we always need conducting material. But what about the other material, metal oxide and non-conducting materials? So that's why we firstly use this IPL. This is a lab, okay? Intensified general pressure lab. So remote process, we simply expose this light on our material. So I'm going to explain 3 case studies. The first case is the white oxide powder. Second one is the graphene oxide, and third one is the carbon nanofibers. Then we demonstrate a binary particle, then also single atom catalyst on graphene, then also 9 element high entropy alloy catalysts are well formed on these carbon nanofibers. So simply, let's compare. The left one is the furnace annealing, right? So there are 5 steps. So we first apply the bias and Joule heating, temperature increase, thermal conduction, and thermal equilibrium, then sample temperature is increased, right? Then right case is the light exposure that we can reduce the steps. So light exposure and generation of the phonon, then after based on phono thermal effect, we can increase the sample temperature. As I mentioned, the left side is a Joule heating, so only conducting material can be used, and also supporting materials should be connected with the electrode, right? And also sometimes chamber system is required because this is really high temperature, then carbon might be oxidized, right? Then on the other hand, this is the IPL, the light exposure. We can simply expose this light on any kind of substrate. Then also this is a non-contact mode exposure. Then air ambient process is available using this IPL. So we use the xenon flash lamp. So as you can see here, this is a 15 centimeter and 7.5 centimeter, the relatively large lamp, right? Then sequential the light exposure is possible using this approach. The first approach is metal oxide. So we prepare 2D tin oxide. Then you can see here platinum, ruthenium, iridium precursors. They are coated on this 2D material. Then IPL, the light exposure, and simply temperature increase up to 1,700 degrees C. Then also rapidly cool down. Then by using two precursors, platinum, ruthenium, and platinum, iridium, and platinum, ruthenium, iridium particles are well formed on this 2D oxide material. And as I mentioned, a sequential light exposure is available, right? So we can use this conveyor belt and light exposure that we can collect, we can synthesize grain scale nanomaterial using this approach. Then let me back to the exsolution. Then I mentioned for exsolution, catalyzed design, we need high temperature, 700 degrees C, the reducing atmosphere annealing. Then I'm very interested in how we can get the rapid speed, the very fast the processing using this IPL. So we prepare, as you can see here, the rhodium, iridium, and platinum doped tungsten oxide nanofiber. Then we simply expose the light. Okay, lattice incorporated fibers, metal oxide fiber. After light exposure, these atoms extrude and segregated, then forming, you can see here, platinum particle and also rhodium particle and iridium particle. Then surprisingly, much improved the gas sensing property achieved using this approach. Then also we can further extended this technique for the single atom catalyst design. For example, using graphene oxide and melamine is known as an N-doping site. Okay, so we prepare N-doped graphene. Then also we mixed this metal ion, cobalt ion, nickel ion, and platinum ion. We mixed all together. Then light exposure, temperature increase up to almost 2,500 degrees C. Then just 0.01 second. Then rapidly cooled down. Then you can see here, this is a nickel single atom, cobalt single atom, and platinum single atom. Also, we can mix two precursors, right? Cobalt, nickel, then we can control the relative amount. Then in this case, 52% the cobalt and 48% the nickel, well formed using this IPL, the light exposure. Okay. Then now we are extending this material for also broad range of application, chemical gas sensors, and also energy application, hydrogen evolution reaction, then also oxygen evolution reaction catalyst. Then also we synthesize 9-element particle. As I mentioned, high entropy alloy particle, the same here. So this is a carbon nanofibers, 6 centimeter and 6 centimeter. Then we measure here, then 5-element platinum, iridium, iron, nickel, cobalt particles are well formed on this carbon fiber by simply exposing the light. Okay. Then also you can see this is a 9-element particle. As compared to the all other synthetics, then we are fastest. Okay, so 0.01 second we can synthesize this interesting catalytic particle. We further change the material, supplement material, carbon nanofibers. This is 9-element. Then also graphene. Then also we use the MAXIM. So that means we can use broad range of the supplement material. Okay. So then now, recently we further extended this technique for synthesis of carbon nano-onion. So actually this carbon nano-onion consists of multi-layers of fluorine like sp2 hybridized carbon. Okay, then it is known to have high specific surface area up to almost 800 meters square per gram. Then also their size is really small, right? Less than 5 nanometer and less than 10 nanometer scale. Then also we can incorporate the heteroatom, single atom decorated carbon nano-onion. Then this carbon nano-onion can be synthesized from the nanodiamond, okay, sp3 hybridized carbon. So as you can see here, this is from the nanodiamond to the nano-onion. It needs very high temperature, over 1,700 degrees C. Then how we can get such a high temperature using IPL? Okay, so that's why we incorporated here the hotspot, high temperature hotspot material, carbon black. Okay, so we mixed the nanodiamond and carbon black, and carbon black temperature increased up to almost 3,000 degrees C. Okay, then they transfer thermal energy from carbon black to the nanodiamond. So you can see here, this is a nanodiamond. Then we mixed we changed the relative ratio between nanodiamond and carbon black. Then eventually we could synthesize nano-onion by simple one-time exposure of the light. Then also we further decorated the single atom catalyst, broad range of single atom catalyst on this carbon nano-onion. Alright, so this is the first part, the take-home message. Then I mentioned host material, graphene, carbon nanofibers, and MXene, the metal oxide. Broad range of various metals, various support material can be used for this high entropy alloy, and also single atom catalyst, and also X-solution catalyst design using photothermal annealing. Then what's the next? So what can you do using this ultra-fast approach? Recently, I won the huge grant, the KAIST the joint research work. Then as you can see here, for the synthesis of the cell, the lithium-ion batteries, then my students are using this argon-sealed glove box, right? So there are a lot of, there's so many human errors here. So one of our colleagues made this automated cell assembly system. Okay, there's also the cell characterizations are conducted within this system. And also now we are developing the autonomous material synthesis using this IPL. So AI-driven materials design. Then after that, we used robot system to develop the broad range of the nanomaterial and also energy device fabrication. Okay, so let me switch the gear to the nanofibers membrane. Actually, our lab is expertise in electrospinning. So electrospinning is a very well likely technology for producing the organic nanofibers and also metal oxide fibers and carbon nanofibers. The electrospinning machine consists of the high voltage power supply. Then also this is a ground plate. Then we need highly viscous polymer. Okay, polymer materials dissolved in holoxylbed. Then under ejection through this nozzle, you can see the color change, right? Blue to white, black to white, and you can see below one is the stitching pattern, KAIST. When dye, once we injected hot water, you can see the color change, right? So using this, we can measure the body temperature. Once body temperature is increased up to 39 degrees C, so we can monitor body temperature. This is a reversible, okay? So we can use this for the temperature monitoring. Another interesting approach is the color change, right? So we can incorporate, dissolve the dye within the fiber. So this is a video of color changing sensor reacting to HCl vapor. Okay, so once exposed to the vapor, toxic gas, then you can see the very fast color changing now we succeed in mass production of this color changing fiber. Sometimes dye is well dissolved in the solvent, but certain dye you can see the particle size is almost 500 micrometer, really large particle. And how we can incorporate such a large particle within such a small diameter nanofibers? Simply that we can break, right? So using the ball milling, that we can incorporate this dye within the fiber, then also outer surface of the fiber. Then this is a 20 ppm, the gas gun exposure. So you can see everybody this, right? It's a kaist, okay? So 20 ppm hydrogen sulfide exposure. Actually, we use the lead acetate dye. So lead can react with the hydrogen sulfide forming lead sulfide. So color changed from white to the dark brown. So simply we can cover the broad range of dye, various dye on these fibers. We can significantly increasing the color changing density. Most common colorimetric sensors using cellulose paper. Okay, so you can see this left one. The surface area is not that high, but in our case, we use nanofiber. Okay, high surface area and high porosity, then we can induce much significant color changing intensity using the nanofibers. So we measure hydrogen sulfide. This is an ammonia case. Then HCl vapor. Then any kind of toxic gases can be detected using this nanofiber technology. Okay, then meet together, then high-speed rotation drum, then after the winding, then we can get such a high density, the nanofiber yarn, okay? Very high density, that means we can maximize color changing intensity. Now we using this nanofiber yarn as a platform, okay? For various sensing application. Simply, we can deposit the ITO, for example. Then this ITO is conformally coated on individual fiber. Okay. Once gas is reactive or absorbed on the ITO surface, resistance change. But there is no selectivity, so that's why we additionally grow the ZIP-8 for selective gas penetration. Then we use this nanofiber yarn for NO2 selective gas sensors. Then also one of my students, now he finished the postdoc at MIT, then joined the Hanyang University. Then he prepared this teaching pattern, okay, H2S and KAIST, right, made by sewing using colorimetric yarn sensor. Then after introducing hydrogen sulfide gas, you can see the color changing from white to the dark brown, okay? Highly selective hydrogen sulfide sensing can be achieved using this approach. Next application is metal oxide. Nanofiber is a scaffold, okay, sacrificial templates. When we increase temperature, we burn out this polymer matrix. Then we like to, before closing my talk, then I'm serving as an associate editor for 4.5 years. Then last July, I promoted to executive editor of ACS Nano. So your interesting, exciting work, the submission to ACS Nano is very welcome. Then I know the next year is Chiang Mai's 60 years anniversary, right? Then also, KAIST is also very young university. So 3 years ago, we celebrate 50 years of anniversary. Then as an editor of ACS Nano, I collected the 14 review article. Then we published special issue. So you can see this is the KAIST campus. Okay, so thank you very much for your kind attention. Then I also would like to thank all our group members and collaborators. And 2 years ago, all our group members visited Malaysia University. Then next time, I want to visit the Chiang Mai University with all our group members. And this is the last